This is Solar Hours by Ari Leopold of Sky Power, Solar Engineering for Arizona. There are many programs out there that help lower the cost of solar with incentives and tax credits. Our cost calculations here today will be based on raw costs and will not be including any of that funding. First, we're going to look at how the units of measurement connect. 1 kilowatt of solar panels with 1 solar hour creates 1 kilowatt hour of energy. Then we're going to be looking at the relationship between the cost of solar panels and the cost of solar energy. The goal here is not to persuade anybody that solar energy is good. If you're watching this, then you're already part of the group that's at least interested in finding out how we can use solar energy. The trend in the cost per kilowatt hour of energy has been that solar energy was expensive but getting cheaper, while coal and nuclear energy were cheap but getting more expensive. We all know that Arizona is very sunny. How much sunlight is there? A lot. Here's a map from the Solar Energy Industries Association in Washington, and it tells us that a lot of sunlight is 2,000 kilowatt hours per kilowatt year. And we're not sure what that means, but at least we can see that our region in the Southwest has the most. Here's a map from Solar Energy International out of Colorado, and this is a map of kilowatt hours per year per kilowatt of photovoltaic panels, which we know as solar panels. As you can see, there are some assumptions about how you're going to be installing these solar panels. You'll also see that this map is numbers of various cities throughout the US, and again, Phoenix has the most at 1,450. We still don't know what that means, but at least we're glad that we have the most. Let's consider it on a more intuitive level. You might say Arizona is sunny just about every day, or it has 330 full days of sun a year. You might say it was sunny for 4 hours earlier today and then it got cloudy. The point here is that amount of sunlight is measured in units of time. So now let's look at these units of measure from those two maps. And although it looks really confusing, in both cases we actually see that the kilowatts on the top and the bottom of the fraction, that's 1 to 1. We can cancel those out, and in both cases we're left with a much more understandable unit, hours per year. So this is consistent with our idea that sunlight would be measured in units of time. The unit here we're talking about is a solar hour, or what you might call a peak sun hour, and it's the number of hours of full sunlight we can collect. Obviously, there aren't 24 of them in a day. The sun's not out for 24 hours. Also, morning, evening, clouds, shade, air density, all these factors give us less than full sun at different times of the day or the year. Luckily for us here in Arizona, all of those factors are less of an obstacle than they are in the rest of the country. So let's turn back to this map from SEIA, and we can see that the confusing unit actually translates to potential solar hours, the amount of solar hours that the sun is shining down that we could potentially collect. Another interesting thing going on here is that solar hours give us a unit of measurement to quantify the solar natural resource we have here in the Southwest, and as we all know, that's going to be a pretty important source of energy moving forward into the future. The map from SEI is starting to make more sense too. This is the average number of solar hours that are actually collected, and as you can see, Arizona is still getting the most in the country. So let's check solar hours off the list. We've seen that that is the unit of measurement for quantifying the amount of sunlight. And let's turn our attention to the kilowatt hour, which is the unit we use to measure the amount of energy. To give you a reference, a kilowatt hour is the amount of energy you would use to cook an extra large deep dish pizza, like perhaps from Pizzeria Due in Chicago, an excellent use of a kilowatt hour. kilowatt hour is also the amount of energy that it takes for a car to drive about 3 miles, and that energy is delivered in the form of, as we know, gasoline. So how much does it cost to buy a kilowatt hour of energy for your home? In order to find this out, we looked at the residential pricing table from APS Power Company, which serves the Phoenix area, and as you can see from this chart, it's very complicated. There is not any one particular price for a kilowatt hour. It changes depending on the time of day and the time of year. Now you'll see the prices range from 5 cents per kilowatt hour to about 25 cents per kilowatt hour. It happens to be more expensive during the middle of the day and the summer months because that's when the most energy is being used. It so happens that's also when we're getting the most amount of solar energy, so we might say that solar kilowatt hours are worth peak rates. But because it's so hard to figure out, we would love to just have somebody tell us an average that we could use. Fortunately, we have a report from the Institute of Local Self-Reliance in Minnesota, and they report in 2011 that Arizona saw an 11-cent average for residential power. This power comes primarily from coal and nuclear fuel sources. From the same report, we have estimates of the average cost per kilowatt hour of energy made from solar. Now, if you take a look in the right-hand column, they say the average cost in the US for a kilowatt hour of solar energy is 27 cents, which obviously is more expensive than 11 cents. It also tells us that the best, i.e. lowest cost for solar energy in the US was to be found in LA, and that it was 18 cents per kilowatt hour. Also in the center column, you'll see reported averages for the cost per watt of solar panels. So we can cross kilowatt hours off our list and get into more detail about watts and kilowatts. What's important about the watts of a solar panel is that it's the unit of measure that we use for pricing. Now, one thing that's tricky about watts is that they're a capacity. They're a maximum possible, like an 8-ounce cup of coffee. There's nothing about the cup that guarantees you that there's 8 ounces of coffee in the cup. In fact, there's almost always less than 8 ounces. Another tricky thing about pricing solar panels in dollars per watt is that solar arrays on houses actually are measured in kilowatts. For example, 3 to 7 kilowatts would be typical for a home array. 1,000 watts is 1 kilowatt, and the only real reason that they do this is because $5,000 per kilowatt sounds expensive, but $5 per watt doesn't sound so expensive. Actually, those two measurements are the exact same cost of solar panels. One useful way to envision this would be to think of kilowatt capacity as like a gas tank, while solar hours is your miles per gallon, and kilowatt hours is how far you can go on that tank of gas. The energy that we buy from the power company is priced in kilowatt hours, yet when we buy solar panels, it's measured in watts or kilowatts, and an obvious question would be, how do we figure out the price per kilowatt hour based on the price per kilowatt? And the way we figure this out is we take the cost per kilowatt of the solar array and we divide it by the number of solar hours we think we're going to be getting from the array. And let's just take a moment to see how we came up with that. Basically what happens is the cost per kilowatt hour of the system is going to be the cost of the whole system divided by the number of kilowatt hours that it makes. Now in line number 2 you see we've broken down the cost of the system to be the dollars per kilowatt times the number of kilowatts, and also the number of kilowatt hours that it makes, we've broken that into the number of kilowatts times the number of solar hours. And what lets us do that is that the relationship we saw before between kilowatt hours, kilowatts, and solar hours is present in this formula on the bottom of the fraction. And so you see there's actually kilowatts on the top and the bottom of the fraction in a 1-to-1. And that's how we came up with the formula. You see in line number 4, the cost per kilowatt hour is the cost per kilowatt divided by the number of solar hours. So what numbers do we plug into this formula? The cost per kilowatt's easy to know, it's how the system was priced. The report said $4.22 was a low, $6.40 being an average. Here in Arizona though, we're finding that $6.40 a watt is actually on the higher side. The average of those two figures being about $5.30 a watt is actually pretty typical for the industry here. What's much harder to know is the number of solar hours we're expecting out of the system. One way to break it down would be to figure out how many years the array is going to last and how many solar hours we plan on collecting each of those years. The utility scale solar that's been going up has a 20-year contract with the power company, so they're expecting it to last at least that long. The solar panel manufacturers are expecting it to last at least 25 years, since that's the warranty that they offer. Will they last longer than that? We actually think so. For all we know, they last forever. But we're going to go ahead and call 30 years a safe bet and move on with our calculations. And as far as how many solar hours we get per year, we actually have a chart for that. That was the map we got from SEI, telling us that we were getting 1450 solar hours per year. So for a range of 20 to 30 years, we can expect a total number of solar hours to be from 29,000 to 43,500, which is a lot. Here's an example of the output data from an actual sky power array. This one's a 3.44 kilowatt array, and you can see in 2010 it produced about 6,090 kilowatt hours. And you'll also remember that the number of solar hours we're collecting is the same as the number of kilowatt hours per year per kilowatt of photovoltaic panels. When you divide them, you see we actually collected 1,770 solar hours. So we're actually doing much better than the average. And more importantly than that, we're showing that it is indeed possible to get larger yields of solar hours. Another interesting consequence being that solar hours per year gives us an objective unit to measure how well engineered a solar array is. And the industry as a whole is moving towards better and better engineered arrays. Even rounding that down to 1,700 solar hours, we would see that in the lifespan window of our array, we can actually expect 34,000 to 51,000 solar hours total. So now we have all the information we need to calculate the dollars per kilowatt hour cost of solar energy. And then when we know that, we'll be comparing apples to apples with our fossil energy. Now recall that the report had given a range of 18 cents to 27 cents per kilowatt hour. The report didn't say how many solar hours they were using to calculate. But when you take a look at the numbers with our formula, you can see they were using 23,700 solar hours, which would be equivalent to 20 years at 1,185 solar hours per year. But there's a twist here. It was somewhat of a pessimistic calculation in the sense that they only calculated for the bottom of the range. There's a mismatch here because we were actually talking about comparing average cost per kilowatt hour. And if you recall, from the power company, we were looking at 11 cents as the average. So to find out the cost per kilowatt hour of solar energy, we take a look at the range of pricing for our solar panels, from $4,220 per kilowatt to $6,400 per kilowatt. And we'll consider the average number of solar hours per year reported as 1,450. Let's also consider the cost of energy for a sky power array collecting 1,700 solar hours per year. Here's the information in a data table format. And as you can see, realistically, the highest we would expect to pay for a solar kilowatt hour would be about 22 cents. We actually think that most of the home solar arrays that are out there are producing energy at about 10 to 12 cents per kilowatt hour. And as the prices come down, you see we're getting energy for about as low as 8 cents. When we graph this data, what we see are the three colors referring to the three different lifespan windows, and across the horizontal, the specifics of the cost and number of solar hours collected by each individual system. And as you can see, compared to an 11-cent retail average from the power company, solar is getting to the point where it is the same or actually lower cost than we have been paying up till now. Now recall, we had looked at the general trend in the cost of energy and seen that solar energy would eventually intersect fossil energy in terms of raw price. And what's pretty significant about this data is that the time where they're intersecting is now. Not only are they competitively priced at this time, but the cost of solar energy continues to drop while the cost of energy from the power company continues to rise. So the money decision for a homeowner to make is solar. The fact that we've arrived at this point also has consequences on the government level. For one thing, when we're looking at the lowest bidder, we should be considering the cost of energy to be the unit that we want to find the best price for. Also, we would want any incentive programs to reward production of kilowatt hours of energy, as does the open market green credit trading that exists in the US but not yet in Arizona. This type of open market also offering the opportunity for Arizona to export its natural solar resource to other states that are pursuing a renewable energy standard. And most important of all is that we're looking as honestly as possible for the best sources of energy that we can use to power our society. Currently, in Arizona, solar is an excellent resource for us to be using. This has been Solar Hours. I'm Ari Leopold of Sky Power, Solar Engineering for Arizona.